For decades, there's been this invisible wall at the heart of our computers, a fundamental speed limit between our apps and the OS. Well, today, we're talking about a technology that doesn't just push that limit, it completely rewrites the rules of the game. This is the story of I/O sharing. And really, this whole revolution boils down to this one simple, really powerful question. Think of the old way, like constantly calling a busy office, asking, is my package ready yet? How about now? The new way? You just drop off a to-do list and say, hey, just let me know when everything's finished. That fundamental shift in thinking is what makes I/O Earring so incredibly transformative. Okay, so here's how we're going to break this down. First, we'll meet the villain of our story, the system call. Then, we're going to take a trip through 4 decades of clever, but ultimately flawed solutions. After that, we meet our hero, I/O Earring. We'll peek under the hood to see how it works, and then we'll wrap up with its huge impact on the real world. Our story really begins with this necessary evil, an operation that's so fundamental but so expensive that it's shaped software design for generations. Let's talk about the system call. So anytime your application needs to do anything real, like read a file or send data over the network, it has to stop and ask the operating system's kernel for help. That request is called a Syscall. And every single time it happens, the CPU has to drop everything it's doing, save its entire state, switch into a special kernel mode, do the work, and then switch all the way back. For high-performance apps doing this millions of times a second, this context switch tax is just crushing. So as you can imagine, for 40 years, developers have been coming up with all these clever ways to try and work around this tax. But as we're about to see, every single solution was really just a compromise, a patch on a fundamentally broken model. This whole journey starts way back in the 70s with the simplest thing you could possibly do, blocking I/O. Your program asks to read a file, and it just stops. It literally goes to sleep, wasting all that precious CPU time until the data finally shows up. Simple, sure, but just catastrophically inefficient. So the first big attempt to fix this was a function called select. It let a program watch a bunch of connections at once, which was cool. But it had some really fatal flaws. For one, it was super slow. The kernel had to scan every single possible connection, even the ones that weren't doing anything. And worse, it had this hard limit, usually 1,024 connections. And if you tried to go past that, it didn't just fail. It could actually corrupt your program's memory and cause these mysterious crashes. It was a ticking time bomb, for real. Then, in 2002, epoll came along, and honestly, it was a game changer. It totally solved the performance mess of Select and became the gold standard for high-performance servers. But it still had this hidden cost. It forced you into this little 2-step dance for every single operation. First, you'd make a syscall to ask the kernel, hey, is anyone ready? The kernel replies, and then you have to make a second syscall to actually do the read or write. At massive scale, that's still a ton of overhead. Now, around that same time, something called Linux AIO, or libao, showed up. It promised to be the true tell-me-when-you're-done model we all wanted, but it was a false dawn. It was just incredibly restrictive. It only worked for storage that completely bypassed the OS cache. It couldn't handle network sockets at all. And get this, even then, it could sometimes just stop and block anyway, which defeated the whole point. It just left the I/O world a fragmented mess. So here it is, the whole 40-year history of compromise, all laid out. From the simple but super wasteful blocking I/O, to the flawed select, to the much improved but still chatty epoll, and the broken promise of Linux AIO. I mean, each one was a step forward, but none of them actually solved the core problem. The world was definitely ready for a real revolution. And that revolution finally arrived in 2019. Look, I/O Earring isn't just a slightly better epoll. It is a completely new contract between your application and the kernel. It shifts everything from that reactive readiness model to a proactive completion model. This right here is the fundamental difference. With epoll, the conversation is this constant back and forth negotiation. Are you ready? Yes. Okay, now do the thing. But with I/O Earring, it's just a single, clear command. The application gives the kernel a complete work order. Here's the file, here's the buffer where the data goes, do the read, and just let me know when it's done. That entire 2-step dance is just gone. This quote just nails it. This is the entire paradigm shift. By moving from "are you ready?" to "tell me when you're done," we're not just saving a step. We are handing over the responsibility for doing the work from our app directly to the kernel's incredibly powerful asynchronous machinery. The tyranny of the syscall is finally broken. Okay, so how does IO Uring actually pull this off? Well, the architecture is surprisingly elegant. It's all centered on these two shared data structures called ring buffers. The core idea is just brilliantly simple. Think of it like a pneumatic tube system, the ones at the bank, between your app and the kernel. The submission queue, or SQ, is where your app drops off its list of jobs. The completion queue, or CQ, is where the kernel sends back the job done receipts. And because this is all in shared memory, there's no expensive data copying back and forth. It's super fast. And the workflow itself is just as elegant. Your application can fill up that submission queue with, say, hundreds of different requests. Then it makes just one single system call to tell the kernel, go. The kernel chews through that entire batch of work asynchronously, and as each job finishes, it just drops a little completion notice in the other ring. The cost of that one syscall gets spread out across all those operations, making the per operation cost practically nothing. But wait, it gets even crazier. For the most extreme latency-sensitive workloads, IO Uring has this special mode called SQ poll. Here, the kernel literally dedicates a thread to just sit and watch the submission queue. Your app can then add new work to the queue without making any syscalls at all. It is the lowest possible latency you can get, a true zero syscall way to submit I/O. So this all sounds amazing on paper, right? But this isn't just theory. IO Uring is already making a massive difference in production. But its journey has been a classic tech story, complete with huge wins and some really serious growing pains. I mean, the biggest names in tech are all in. High-performance databases like ScyllaDB are using it to push storage to its absolute limits. Cloudflare is using it to handle just an insane amount of network traffic. And Meta, where its creator actually works, uses it all over their massive infrastructure. These are companies where every nanosecond of performance counts. But all of this immense power and complexity, it came at a cost. Early on, IO Uring became a massive target for security researchers. Get this, in 2022, Google reported that a staggering 60% of all the kernel exploits submitted to them were targeting this one new subsystem. That created this really powerful narrative that IO Uring was fundamentally insecure. The reality, though, is a bit more nuanced. It turns out that most of those really severe bugs were tied to an early, flawed design that was completely reworked and fixed in kernel version 5.10. The interface has matured a ton since then, and while no software is ever perfect, it's now considered just as secure as any other complex part of the kernel. It really was a baptism by fire. So, after surviving all that, what does the future look like? Well, IO Uring is proving to be way more than just a faster way to do I/O. New features like multi-shot operations, where you can submit one request to accept all future network connections, are radically simplifying server code. The kernel isn't just a gatekeeper anymore. It's actually becoming a programmable, asynchronous platform in its own right. And that leaves us with this final, really provocative question. For decades, the heart of every high-performance server has been this complex event loop that runs in the application itself. But with a kernel that can now manage all these long-lived asynchronous tasks on its own, is that entire programming model maybe becoming a thing of the past? IO Uring didn't just give us more performance, it's forcing us to rethink the very nature of our software.